Okay, well, if we really think that climate change is happening, there might be some short-term weather events that would act as signs and symptoms of the longer-term temperature change. So if you think about the most expensive hurricane disasters of the last 117 years, when do you predict that the most expensive hurricanes have occurred? Is it randomly? That is, there's no correlation between weather related patterns and time? Or do you think that the most expensive ones happened recently because we've had an increase in the number of people and buildings on the coasts? Or do you think that the most expensive ones have happened recently because hurricanes are becoming more frequent and more powerful? Or do you, and this should say D, do you think both B and C have been factors? Well, I hope you said both B and C. It's true that we have more people and more expensive buildings. However, the hurricanes are becoming more frequent and more powerful. All right, we can also look at temperature and drought conditions, and we would see that for 2018, the summer was tied for the fourth hottest summer in the last 120 years. But what you don't realize is that three of the other four hottest summers were in the last decade. So the International Panel on Climate Change was tasked, an international group of scientists was tasked with informing policymakers. And here's one of the things they said. There is high confidence that the ability of many ecosystems to adapt naturally will be exceeded this century. Unmitigated climate change would, in the long term, be likely to exceed the capacity of natural, managed, and human systems to adapt. Okay, and here's what the news was like in December of 2019, just this past winter. Australia was having tremendous heat waves, and we know about the heartbreaking fires that happened. So I just want to make sure that we understand what these terms mean. Resilience, can we bounce back from some terrible event? Adaptation, can we change our infrastructure, the way our communities are laid out, the way our houses are, or our personal habits to cope with rising heat and extreme weather? Mitigation, to make less severe or less harsh. In this case, what we mean is we have to reduce carbon dioxide and methane emissions. So how can we do this? We can change to green sources of energy and conserve energy better. We can update our electrical grid. That would be wonderful. We can reduce CO2 from transportation, energy production, and industry. We can remove CO2 actively from the atmosphere, but so far this is a slow process. So we must adapt our infrastructure to cope with severe weather events. But there are some ways that we have been talking about a technological fix for this problem. One of these, and these would be global scale, regional scale, national scale solutions. Geoengineering of the atmosphere is a global scale fix. It could be instituted actually pretty cheaply by a single country. But of course, it would not be ethical for one country to decide what the world's atmosphere should be. So ideally, we would get political international agreement if we decided to geoengineer the atmosphere. Carbonate mineralization is another possibility, rock carbonation. There's also CO2 storage in old, depleted oil fields, and that's a third possibility. I want to go back and talk first about geoengineering of the atmosphere and make sure we understand how this would work. And then at the very end of this, I'll talk about good news, different adaptations and mitigation actions that we can all support. Okay, very quickly, you know what the atmosphere consists of, mainly nitrogen. The greenhouse gases are in purple, and they're the smallest piece of the pie in terms of their abundance, but we've already seen that they have the biggest effect on temperature. Where do they come from? Coal. The preparation and the construction of cement, that's sort of weird. But anyway, concrete and cement production create this. Airline flights produce a tremendous amount of greenhouse gases. And then, of course, cars. What happens once we've produced these greenhouse gases? We have incoming solar radiation, and not all of that radiation reaches the Earth. Some bounces off the various layers of our atmosphere. Some can bounce off the land and return to space. What we're concerned about is that the land radiates infrared light, and that is then absorbed by greenhouse gases in the atmosphere and sent back down to the surface. And so we have a feedback that causes things to warm up. Let me break this down even further. Incoming sunlight, if we look at it, we think of it as being in the visible spectrum and creating the colors we see. And that spectrum is at about 4,000 angstroms. That really should be 4,000 milliangstroms. Anyway, all right. So notice that that vertical bar goes all the way to the top because it's showing a really high energy flux. And so the blue line maps out the wavelengths of light making it to Earth. We have most of that light in the visible spectrum, but there's also ultraviolet light making it to Earth from the sun, as well as infrared light. That light penetrates easily through our atmosphere. But what happens, and think about an asphalt street in the summertime, that asphalt gets too hot to walk on in our bare feet. Even a cement sidewalk can get quite warm to the touch. And that's because those surfaces are absorbing some of the sunlight, and then they are sending heat back out. And that Earth radiation is here in the red line. And it's shifted to a different series of wavelengths. It's shifted towards the infrared. And that Earth shifted light, totally naturally, unavoidable, is the wavelength spectrum that is strongly absorbed by our greenhouse gases. So that causes great warming in the troposphere. So if we take a look at how much sunlight is coming in, this is a summary diagram. Incoming solar radiation, 340 watts over 1 square meter. That's if we had that square meter at the top of our atmosphere, like up where our International Space Station is, and we can measure that amount of energy coming from the sun. And we saw already from the Bloomberg summary that that doesn't change very much. That incoming sunlight has a variety of things happen. It can be absorbed by the surface, reflected by the surface, reflected by clouds. And we've just talked about how the surface radiation, that is, it's temporarily absorbed and then given off, that surface radiation gets absorbed by the atmosphere. Not all of it. 398 watts per meter squared are given off, and 40 of those watts go directly back out to space, making us look like that blue marble that we are compared to our vast solar system. But 358 watts per meter squared are absorbed by the atmosphere. And the atmosphere wants to do something with that energy. And it has two choices. It can emit that energy back out to space, and it does. But the vast majority of that radiation from the atmosphere comes back to the surface. The problem with that is, as the surface warms, it starts to contribute more greenhouse gases. Warming of the Arctic permafrost actually sorry about that. I'm constantly hearing feedback in the speakers that I'm using for my microphone. It's really annoying. It's delayed. It's like a bad telephone call. Okay, the Arctic permafrost warms up. It has frozen methane in its ice. But once it's warmed, it allows that methane to escape and join the atmosphere, which is then going to absorb more heat energy. This is what we call a self-reinforcing feedback loop, and it is magnifying our problem because more methane in the atmosphere traps more heat, sends more heat energy down to the Arctic, and then we get more methane released and put back into the atmosphere. I want to get to, because we're going to talk about albedo and geoengineering, the amount that's reflected. The reflectance of light is called albedo. And in the past, a lot of incoming solar radiation was reflected by ice on Greenland, ice in the northern hemisphere, ice on Antarctica, and Arctic sea ice. But of course, what we have seen, if we compare 1984 to March of 2018, is that our old sea ice is diminishing rapidly. And we believe that the Arctic will be without ice in the summer regularly from now on. Atmospheric geoengineering takes on this idea of albedo. Clouds have a high albedo because they're white, they're very reflective. Glaciers have high albedo, as we just mentioned. So this geoengineering idea is, can we reflect the sun's energy before it gets to the surface and turns into problematic infrared heat and light? Okay, you've all seen the layers of the atmosphere before, I hope, but this is just a review. We've got the land surface at 0, and then our altitude or elevation into the atmosphere above us is on the y-axis. And you've got that in miles on the right-hand side. If we look at temperature at the surface, we think of this as being around 18 degrees centigrade each year. That's averaging summer, winter, and we're worried about how that'll go up. Well, if you were to drive to the top of the mountain, you are getting further and further away from where we have most of our heat energy trapped, and the temperature goes down. If we fly in an airplane, the temperature goes down. Okay. In the stratosphere, temperature starts to rise again until it's hottest up close to where the boundary between the stratosphere and the mesosphere is. But in terms of ecosystems and humans being harmed, we're really interested in the troposphere. And keep in mind, the troposphere is an idea that came about because we can actually see it. At sunset, we can see the line that forms here between the troposphere and the stratosphere. We can also look at thunderclouds, cumulonimbus, or so-called anvil-shaped clouds, and that cloud flattens out at the tropopause, that boundary between the troposphere that we experience and the stratosphere. So the idea of atmospheric geoengineering is we need to create this barrier in the stratosphere so that the troposphere will cool down. Why do we think this would work? Well, we see that it works for some volcanic eruptions. If a volcano, like this one in the Kurile Islands, emits a large pulse of sulfur dioxide, that sulfur dioxide creates sulfate and sulfuric acid droplets. And that has high reflectivity, high albedo. So our incoming light in yellow reflects back out before it reaches the surface. However, we know that for powerful eruptions, this reflectivity only lasts a year or two. There are some advantages to atmospheric geoengineering. We can create a sulfate barrier. It's relatively non-toxic until it starts creating sulfuric acid. And we could send planes up and create these aerosols, and it would cool us down. It's relatively cheap, easy, and fast, but there are some problems. There are many disadvantages. Scientists, especially geoscientists and atmospheric scientists, have a lot of concerns about this because atmospheric circulation is very, very complex. We could actually cause part of our atmosphere to be lost to space. We could actually cause a cascade of cold air coming from the stratosphere to the surface. So this would very likely create extreme weather events. The other thing is our geoengineering barrier would have to be continued forever, or at least until we could start removing our greenhouse gases. Right now, the assessment is that the disadvantages outweigh the benefits, and that this is a dangerous solution. But research is still being done for this as a last case option.